Hi guys, today I'm going to explain how to evaluate the scattering and the extinction cross-section of a silicon nanoparticle. In fact, we're going to work in the infrared between 1000 and 2000 nanometers. I'm going to use one very famous paper, this one, the strong magnetic response of micron silicon particles in infrared, by Garcia Charri and Professor Juan Jose Sainz from Autonomous University. And we're going to reproduce this curve, the scattering cross-section divided by the radius of the particle of a silicon nanoparticle with 230 nanometers of radius and a refraction index of 3.5. This is something like an epsilon of 12.25. And we're going to reproduce this black curve. This black curve is the Mies solution. And we're going to do it with Comsol 5. Pause. I recommend you to, if you have any questions, technical questions, the best option is to study Bohren Huffman, chapter 4 and chapter 5, that explain in detail this kind of this problem in particular. Okay, now that I already explained the problem, we're gonna evaluate the scattering and the absorption cross-section of a dielectric nanoparticle in Comsol Multiphysics. So let's start. Let's open Comsol. And here we are. Comsol 5, last version of Comsol. And we're gonna start by defining the global parameters of our problem. But before this, we're gonna specify our problem. We start by 3D system. We're going to work in a 3D system, and we're going to work with electromagnetic waves at frequency domain. Of course, if they are not recently used, you can go to radio frequency and electromagnetic waves frequency domain, or you can go to optics, wave optics, electromagnetic waves frequency domain. Okay, we're gonna add, and then we're gonna study it. And we're gonna study the frequency domain, and it's done. Okay, so now the system is generated. As you can see here, you have the controls to configure the screen. Here, this part of the screen. Here, you have the model builder. And here you have the options. You have definition, geometry, materials, physics, math, study, results. And every time you click in one of these menu changes. Okay? So we start, like I already told, we're gonna start by defining the global parameters. The parameters that are gonna be always the same during the problem. So we're gonna start by clicking with the right button. Every time you see this window opening, we are clicking with the right button, and we click in parameters. Okay. So I have a list here, and we're gonna start by the electromagnetic field. Okay, I'm not gonna explain in detail each of these parameters, because I suppose that you already studied this problem from the theoretical point of view. So the electromagnetic field is going to be 1 volt per meter, and we're gonna here introduce the description, and we're gonna call it electromagnetic field. Now we define the radius, and the radius is going to be 230. Here we don't put the units. We don't need to put units. We will put them later, and it's going to be the radius of the sphere that we're going to study. And like you probably should know, we should have the perfectly matched layers and these perfectly matched layers must have a radius. So we're gonna define the radius of the PML, and it's gonna be something like 10 times the value of the radius. Okay? And we're gonna say that is the radius of the PML. Also, the thickness of the PML, I suppose, like I already told you, that you know what is the meaning of perfectly matched layers, what is behind this. If you don't know, you can start by searching on Wikipedia, but there are lots of books and papers that describe very well these perfectly matched layers. So we're gonna say that it's gonna be something like 3 times the radius, and we're gonna say that this is gonna thickness of the PML. No, I'm doing it in a clean way. Okay, lambda, because we're gonna scan the wavelength of the incident electromagnetic field, and we're gonna start with 1000 nanometers. Okay, initial wavelength, and we're gonna use this as a variable. So we must also define a lambda minimum. It's gonna be the same value, 1000 minimum, or initial wavelength, and we're gonna have lambda max 2000. Lambda max 2000. It's gonna be the final wavelength. Okay. So you're gonna start to scan from 1000 to 2000, and the step is gonna be lambda step, and it's gonna be 5. Wavelength step. Also, we're gonna define the geometrical cross section, and as you know, in a sphere it's gonna be the area of the sphere. But the area, this time we're gonna put units, and as you can see, I forgot the multiplication signal. Okay. We're gonna put a geometric cross section. I'm sorry for my English. And we're gonna do it. Also the normalizing parameter. Once again, you should read Bohren Huffman, chapter 4 and chapter 5. In fact, you should read the entire Bohren Huffman. Really nice. Okay, and that's it. These are the global parameters. So we start by defining the global parameters, and then we're gonna define the geometry. And we need to first, it's gonna be in meters. No, we want to work in nanometers. And we want to add a sphere. Okay, this is the sphere that in our case is going to be a silicium sphere. Okay, we're going to call it silicium sphere. It's going to be solid, and we'll have a radius already defined before. Okay, and that's it. And you have a sphere, very simple. Now you build all the objects, and you can see here the sphere. Quite nice, huh? I don't know if you know how to use these kind of controls, but it's very, very simple. In fact, when you see this one, select and hide. If you click here, you can hide an object. And if you want to restore all the objects in the screen, you click here. Okay, very simple. You can also do with edges. You can select boundaries. You only need to put the mouse here, and appears a box with a legend. Okay. Also, if you want to select plane views, you can do it from here, zoom, and rescale. We're going to use rescale in a moment, because now we already have the sphere, but surrounding this sphere, we're going to put the perfect matched layer. So we're going to have a new sphere. Okay. This time we're going to have the radius of a perfect matched layer, but it's going to be a core shell sphere. Okay, with thickness of the PML. These values, like I already told you, were defined before. Okay, we're gonna build the objects, and now, bam, everything gray. If you click here, it's gonna readapt the zoom. Okay, if you want to see it, and I select this one now, the boundaries, and you click here, you can see that this part describes the perfect matched layer. Then you have inside the particle. Okay, very, very simple. Comsol is very interesting because define not only volumes but also boundaries or surfaces. It's quite interesting. Okay, we have how the geometry already defined, but we must call to the geometry, to the volumes, we must give them names. Okay, for example, to this particle, this small sphere, we want to call it a nanoparticle, for example. Or this particle, the external shell, everything here is gonna be the perfect matched layer domains. Okay, so let's start by defining what is the physical domains. The physical domains is this empty space, okay, as you can see, surrounding the particle and the particle. These are the physical domains. So when we now click on definitions, and we're gonna here, as you can see, this one explicit, and we click it. Okay, we click it, and we can say that the physical domains are, let's make a review, let's start by hiding these parts, and now we select once again this eye with something inside, and we're going to select this volume, and as you can see, it's already selected here, and we click once again here, and now we're gonna select the particle. Okay, and now we have 5 and 6, and we're gonna call it physical domains. All right, very simple. These are the physical domains, what I select, but we're gonna select the perfect matched layers domains. So we're gonna select the complement because it's everything except the physical domain. So we click here, we're gonna call it domains. I think that you already understand the idea. So we're gonna now select domains, and it's the inverse. Okay? So, and that's it. It's already added. We're gonna select also one call it nanoparticle. We're gonna call it nanoparticle, and now we must select the nanoparticle. So we must hide everything that is surrounding the nanoparticle. And here you have the nanoparticle. We must click here and then here, and it appears here. Nanoparticle. Very, very simple. We must also add the nanoparticle surface because we want to calculate the scattering and the absorption cross section. So it's going to be the surface. So now we're going to here to geometry entity level, and we select boundaries, and now we're going to select, let's make a zoom, we're going to select the surfaces of the nanoparticle. Okay, and we're going to call it nanoparticle surface. Alright, we have the nanoparticle surface, and now we must add the external and the internal surface of the perfect matched layer. So boundaries, and let's select once again. Did you saw what I've done? This one, okay, and it's gonna be this one. You click, as you can see, you click and select, and it's gonna be we will call it external PML surface. Be careful, boundary, not domain. Okay. I'm telling you this because I usually made this mistake. Let's change again because now it's going to be the internal perfect match layer surface, okay? Internal PML surface, okay? So what we must do is hide the external surface. Oh yeah. As you can see, you can do it easily. And let's select. Right, very simple. Everything is selected. Okay, so it's done. It's done. We have the physical domains, the PML domains, the nanoparticle surface, the external PML surface, and the internal PML surface. Okay, it's done. We already defined the geometry, and we give names to the different parts. So now what we must do? We must define the materials. Okay? Very simple. The only problem is that my document is not numbered. So before this, we want to define the perfect match layers. Okay, we're going to definitions, and we're going to say, as you can see here, you have this icon. It's called perfectly matched layers, and you click on it, and now you have the perfect match layers. We're gonna select the PML domains. That's the reason why we call to these names. Due to the symmetry of the problem, we're gonna work in spherical coordinates, and the PML scaling factor, we're gonna put it something like 0.5. Okay, very simple. Okay. I have here in this document to not forget of anything. Okay, so now we're gonna add the materials. Very simple. So we're gonna start by saying that everything add materials. As you can see, I click here, add materials with right click. Gonna build in, and we're gonna say that everything is air. We're gonna right click on air and add to component one. Okay. And at this moment, everything is air. But we're gonna say that the nanoparticle is made of silicium. So what we're gonna do, we're gonna work in the range of 1000 and 2000 nanometers. And as you know, this kind of material is constant in this range. Epsilon is something 12.25. So you're gonna add a blank material, and here we have the material. We're gonna call it Si. It's gonna be a domain. It's gonna be the nanoparticle that we're gonna have, and now we have the relative permittivity. That's gonna be 12.25. Don't forget that Comsol. Imagine that the material has some absorption. This material doesn't have absorption, but imagine that there is a material with 0.1 of absorption. I should use the inverse signal of the complex numbers, because I don't know why, because these guys are engineers, and usually engineers like this notation. So relative permittivity is going to be 1, and electrical conductivity is going to be 0, and that's it. It's not, some people complains that doesn't appear this menu, but appears the refractive index. If so, you must click, let me see, you in wave equations, and you must change the relative, in that case, you must be selected the refractive index, you must change the relative permittivity. Okay, but if you are okay, don't do anything. So it's done. So now you have the geometry defined, you have the materials defined, also the parameters, and now we're gonna characterize the electromagnetic field, incident electromagnetic field. So we start by clicking in the electromagnetic waves frequency domain, and we want to solve to scattered field. Okay, We're going to say that the polarization is going to be in the x axis, like here. And it will come from the negative to the positive zeta direction. So we're going to must put the inverse signal, okay, to pi divided by lambda, this time in nanometers, multiply by zeta. Okay, very simple. If you know physics, you know what this means. If you don't know, don't use Comsol. And that's it. We already defined the wave equation. And we're gonna also click on the electromagnetic waves frequency domain with make a right click. And now we're gonna select scattering boundary conditions, like this one, okay. And we're gonna here select the internal perfect matching layer. Okay. Very, very simple. And now let's triangulate. Let's discretize the system under study. Okay? Let's discretize. And this is the part, the mesh part. And we are almost finishing. Huh? It's very simple. So we start by triangulate the external surface of the PML. So we right click and we're gonna to more options and free triangular. And we're gonna select the boundary and we're gonna select the external PMLs, and it's already selected, and build all. As you're gonna see, you should see here. Oh, it's iron, sorry. It's iron. Yeah, as you can see, the external surface of the perfect match layers is already discretized. If you want, I can repeat it. Okay, I'm gonna repeat it. I'm gonna delete this part, what I've done, and I'm gonna once again. This is the, as you can see, you have the particle here inside, and I'm gonna discretize the external surface of the perfect match layer. So it's going to be external perfect match layer surface, and I'm going to build, and that's it, as you can see it. Very simple. Also, I'm going to swap the perfect match layer, so I'm going to right click here, and I'm going to click on swap, and then I'm going to select here the domain, and it's going to be the perfect match layers domain. And then, once again, I'm going to right click and click on distributions, and it's going to be 5. Now, look to this area. I'm going to build, and this area is divided in 5 parts. 1, 2, 3, 4, 5. Okay, very simple. I'm going to mesh. Click now in mesh, right click, free tetrahedral, and then I'm gonna to right click on free tetrahedral size, and I'm gonna define the quality of the elements. I'm gonna put 5 because it's more than enough. Okay? Very simple. I'm gonna build, and you can see the particle. It's already discretized. Now, but like I already told, we're gonna do a scan of lambda. So we right click on study, and we're gonna put parametric. As you can see, I click on parametric swap. So I'm gonna add, like clicking here, and I'm gonna vary lambda, and it's gonna, we should write here range from lambda mean to lambda step, from lambda mean to lambda max, and between these two you must define the lambda step. Okay, very simple. And now you must say to the program that you're gonna scan in frequency, no? And which frequencies? It's gonna be c divided by lambda, as you know, and c is the speed of light, and it's already defined in the program, so you only have to write c const divided by lambda. That's gonna be swapped, and lambda is in nanometers. Okay, the program is completely defined. You only have now to do one thing, because you want to evaluate the scattering and the absorption cross-section, the scattering and the absorption cross-section. So you must define the scattering and the absorption cross-sections. Also, you must do two different integrations. So you now click here on component, and you're gonna define. Okay? You click here, and you're gonna integration. Here is in component couplings and integration. Okay? And we're gonna int vol. Okay. All right. And the domain is going to be the nanoparticle. We want to integrate in the nanoparticle. And it's done. And you repeat the procedure, this time here and here. And you're going to hit serve. And you're going to integrate in the surface. No, it's not going to be the domain. It's going to be the boundary. And it's going to be the nanoparticle surface. Okay? Boundary, nanoparticle surface. Very simple. Okay. Now you right click on definitions and you click on variables. Okay? And you're gonna do it like okay, so you're gonna write this. Okay, you can copy. It's very simple. Once again, you should read Bohren Huffman if you don't know what we are doing. And that's it. Very well. You're gonna sigma scattering extension. Oh, I'm not writing, as you know. This is the scattering cross section. If you're doing this, you will know that you must integrate in the surface. Vector divided by this parameter already defined at units of area, and this one in top vol. This is the absorption cross section, and you know that sigma extinction, but you can calculate it also. But this is a very simple tutorial, only to you to understand how to calculate extinction cross section. And as you know, you can sum the scattering and the absorption cross section, that you will have the extinction cross section. And that's it. Everything is defined. Okay, I love to do one thing more. I like to normalize the scattering cross section. Now I like to divide it by the geometry cross section. Sigma geometry. All right. And that's it. Everything is done. Now you click on study and you can compute. Okay, I will back when the program finishes. Alright, now that the program already compute the results, you can see here this color map with the fields, with electric fields. And you can choose here for different wavelengths, as you can see here. For example, at the electric dipole, you can plot it. And you can see the electric dipole. Oh, interesting, eh? Okay, don't forget that we are reproducing the results from this paper, the strong magnetic response of submicron silicon particle in the infrared, from Aichol Garcia-Charri and Professor Juan José Sainz from Autonomous University in Madrid. It's an optics express. I'm gonna give the reference in the end, and we are reproducing this black curve, the scattering cross-section of the particle already described, but this time with me. Here this problem is solved considering the Mie expansion, the Mie solution. So you can see the Mie expansions, the red, the green, and the yellow, that this one corresponds to this peak corresponds to the magnetic dipole, this one to the electric dipole, and this one to the quadrupole, the magnetic quadrupole. Okay, you can see it clearly. For example, this one, we're going to the program once again. We're going to the frequency 1150, the one where we could see the quadrupole, and now you plot it, and ta-da! Interesting, eh? Very interesting. Okay, but what we want to evaluate is the scattering cross-section. So what you're going to do is click on results, and now click here in this 8.5. It is the global evaluation. I already clicked before, and appears this menu. You choose the study as parametric solution, and you write here the expression. You want to evaluate the sigma scat, like we already defined it before, okay? And we evaluate, and it takes a little bit long. That's the reason why I already made it. And then you can plot it, and you can see the same curve. I don't know why, but sometimes appear this kind of peaks, like 0. You can reevaluate when you see something strange like this. You reevaluate, and these peaks will disappear. And that's it for the moment. Okay, thank you. Bye-bye.